now we are going to talk about stability criteria, okay, and we all are aware of stability from the mechanical perspective. So, for example, for an equilibrium system, a ball would be stable in such a scenario, and this is, let us say, a function represented by energy variable, okay. Then you could have other scenario, something like this, something like this, something like this, okay, something like this, okay. Now, of course, we know that if this is a energy profile, then of course, in this case u, the first derivative of u is going to be 0, okay. This is not a sufficient condition, and then you need to come up with another one. So, u equal to 0 and u double derivative should be greater than 0 in order to have a minimum, okay. So, this is not sufficient. So, in this case particularly, you know, this is going to be if you perturb slightly, is going to move to this direction, okay. So, this becomes a limit of stability, okay. Beyond this is unstable, okay. If you change a little bit curvature, is going to be unstable. So, there is a limit up till where it can reach, or there is a limit which is defined by nothing but, in this case also is defined by the second derivative of u to be 0, where you can say this is the region of beyond which there is a region of unstable or instability will arise in the system, okay. So, the limit is given by basically these two conditions. So, this is the limit of stability. Again, if you look at these variables, this one first derivative is 0 and as well as the second derivative is greater than 0. In this case also the first derivative is 0 and second derivative is also 0. So, this brings a condition that beyond this of course is going to be unstable, and this is what we are going to use it. So, let me just consider a simple example. We will just take it u first, that u is a function of SVN, and what we are interested is basically for the case of a stability we need the second derivative has to be greater than 0. In other words, we need this condition, all right. Now, since this is a function of SVN, I can write this as sum of various different second order derivatives okay, plus 2 times the mixed derivatives. Just for the completion I am going to write it. Some of you already know this, but is just to make sure that we are on the same plane, okay. Now, what we are interested is that this expression of course is greater than 0, and if one of the variable is, or let us say keeping the two variables fixed, if one of the variable is positive, or if we are changing one of the variable keeping the other fixed, for example, if we are changing s keeping v and n fixed, then this means that this second derivative will be greater than 0, okay. Similarly, if we are keeping s and n fixed, this means this has to be greater than 0, okay. So, using these concepts you can come up with this expression. This is nothing but del t by del s, because del u by del s is nothing but t, and this is nothing but t by Cv, and this has to be greater than 0, which means because t by definition has to be greater than 0, which means Cv is greater than 0, okay. Similarly, you can show del u by del v is minus of del p by del v that means sign has reversed. So this shows that the pressure, if you change the, if you increase the volume, the pressure will decrease. Okay, you can also write this expression as del P by molar volume. Okay, we are taking the N inside, which means basically everything is in the molar quantity. Okay, the other thing is chemical potential. This has to be 0. So if we increase the amount of moles present in the system, the chemical potential should also increase. That is what it tells. That's a condition of stability. Okay. If the chemical potential decreases, which means it's basically unstable. That's what it tells you that. Okay. So it gives you the behavior. So if somebody is ask you what will be the condition of stability for the pressure, if you the volume is increasing, automatically it means something, that the pressure would decrease. Or the way, if the volume is decreasing, which means the pressure is also increasing. So there is intuition for you, and then there is a thermodynamic relation which also tells you the same thing, right? Okay, I can actually extend this exercise for other cases. So I am not going to derive anything. For the case of TVN, okay, del of square A must be greater than 0 for stability, which means del square, for the case of, let us say I am keeping temp T and N fixed, it means del P by del V Tn should be less than 0. It gives you the same expression. It gives you the del P by del V at T is greater than 0, exactly the same expression, what you have got another way. For the case of PSN or SPN, you can show that this will lead to the expression Cp greater than 0. For the case of TPN, you will get del square G del N. For the case of, let us say, binary mixture, this must be greater than 0, which means basically tells you that to greater than 0. Okay. So this is, let us say, for the binary mixture. Okay. So these are the analyses you can do in order to find out the variables for the stability, and this is extremely useful for calculating the phase equilibrium for mixtures. You will be using this information to find out which region is basically stable region and which region is unstable region. Now I will try to ask a question here with an example, that now that you have got this expression, depending on what variables you have kept, you got various different expressions, right? So there has to be some equivalence of the expressions. So irrespective of whatever the variables you fix, some expression should be same. So this we can illustrate by an example. So the question is how to demonstrate equivalence of stability criteria. Okay, and what we are interested is to show that does this expression and this expression are equivalent. Okay. So if one of them is 0, the other one should be 0, something like that. So this is to show these two are equivalent, saying this is equivalent to saying this, the other one. So we will try to solve this. Okay, and again we have to go back to the basic definition. So this is nothing but del square H by del S square, because this is del T by del S at constant P. So I will just consider for the pure system, and which is del square H by del S square at constant Pn. Okay, and this is nothing but del square A by del V square constant T. Okay, so what we are trying to do here is we try to make use of the fact that there is an entropy which is coming here in this expression, and so we can try to introduce entropy in and relate this expression to the entropy changes in the entropy. So that means introducing a new variable, which we can do that using chain rules. So del p by del v at constant t can be written as del p by del s at constant t and del s by del v at constant t. Okay. Now we have these p s t. We have three variables. So now we can use x y z minus 1 rule. Okay. So we have del p by del s t, del s by del t p, del t by del p. So this must be p s s t t p. This must be minus 1. Okay, this must be minus 1. So now from here I get del p by del s at constant t Okay, so with this I plug in here, okay, and this expression can be now replaced by this. So I get del p by del v at constant t is minus del t by del s at constant p, del p by del t at constant s, and del s by del v t. Okay, so I have this expression. Now this is what we actually wanted to get, because you see this was this expression and this part was del t by del s at constant p. So we got an expression which tells you this left hand side is proportional to t by Cp. Okay, so this is what our intention was, to get del p by del v t is proportional to del t by del s p. Okay, so this means that this condition of stability criteria, or the stability criteria, is basically are equivalent. Okay, if one is 0, basically the other will be also 0. Okay. Now this criteria are quite important also. So I will just make use of this criteria for understanding the criticality also, and then we will stop this lecture. So let us take a case of vapor liquid two phase system or vapor liquid phase diagram on a PV diagram. Okay. So this is our binodal, or this is the basically the saturation vapor and liquid lines. Okay. I can draw the isotherms. Okay. So this can actually go here, and it may not directly reach to the other part, because it could, depending on the rate at which you are controlling the experiment, it can actually go into these regions. So what we see is the following. Okay, something like this. This is one temperature. Okay, and similarly this as another temperature, and so forth. You will get this, which is a critical point. Okay, so this is sometimes called binodal. These lines, this green curve is called binodal. Tie lines can be drawn on this, and then there is something called spinodal. The spinodal actually is the one where you are getting this point where this part is reaching minimum. Okay, that means, and this is the region where this is maximum. Yeah. Okay. So this is your spinodal. So what you see from this part to this part is there is a slope is positive. At constant t. When slope is positive, what it means, from our condition criteria, the del p by del v should be less than 0, which means this is the region where it is unstable. Okay. So, what we did is the case where this is 0, this point del p by del v is 0 here as well as here, because that is the minimum and that is the maximum. So, we are trying to connect these dots. When you connect, we got this blue curve, and this becomes the limit of stability, okay. And this region is your metastable region, and this region is unstable region. Okay. And this is a critical point. At critical point, we know the first derivative and second derivative has to be 0, right. So, del p by del v at t is equal to del square p by t, right. Now, we also know that these two terms which we just derived, that t by Cp should be greater than 0 for stability, and as well as del p by del v should be like less than 0. So, this must be an equivalent stability criteria, okay. But at critical point, what happens? This is 0, which essentially means at critical point, since these are equivalent criteria, at critical point, if this is 0, implies Cp should go to infinity, right. Cp should be infinity, okay. So, if you measure Cp as a function of temperature or function of this, that at critical point you should see it should increase to very large values, right. Now, what happens to also in at near critical point, that fluctuations, okay, the density fluctuates, any thermodynamic properties fluctuates which are not controlled. For a temperature, volume and n fixed, other thermodynamic variables should fluctuate. So, at critical point the density fluctuations are quite high, okay. When you keep the temperature below, let us say, a critical point, the fluctuations are smaller or equivalent to its molecular diameter, and that is why for a two-phase system you see very clearly the separation between two phase. But now when you take the temperature to the critical point, what happens? The fluctuations are much more than the molecular size. So, they fluctuate so much that at critical point they overlap. The one phase is fluctuating. So, when they overlap, the distinct boundary is lost, okay. And that is where this milky appearance comes into this. If you do an experiment, you can easily find out the phase separation by looking at just an image of it below critical point, but at critical point you will not be able to find any specific phase separation. So, the reason why we went through this, we wanted to understand the stability criteria and its usage in various different applications. There is equivalence of criteria, and thus this leads to certain conditions, okay, which we can make use of to find out whether the system is stable. Though I have explained it in terms of only the pure system, but of course you can extend that to also mixtures. So, we will stop here, and we will continue in the next lecture where we will describe a bit of equilibrium conditions, okay, that gives you a phase rule and so forth, okay. So, I will see you in the next lecture.